Hey everyone, welcome back to Math with Vanj. I'm Vanj, I'll be teaching you math, obviously. So in the last video we covered some of the different properties of limits and also how to solve for them algebraically. In this video we'll be covering the different types of discontinuities and also defining continuity at a point. So if you're ready, I am too, let's get started. So for the different types of discontinuities, there are two main types. We have the removable discontinuities, and these look like kind of like holes on a graph. So they're like holes on a graph. And then we have the non-removable discontinuities. Non-removable. And there's two different types of non-removable discontinuities. There are the infinite discontinuities, and there's the jump discontinuities. So let's get a better idea of what each of these are. So let's look at an example of a removable discontinuity. So here we have the function graph f of x equals x squared minus 1 over x, this should be minus, over x minus 1. So, and this graph looks like this, and as you can see, there is a hole at the point 1, 2, right? And that's the removable discontinuity right there. But why is it removable? So if you factored this function, you would get x squared minus 1 factors into x plus 1 times x minus 1 all over x minus 1. And as you can see, the x minus 1s on the denominator and the numerator can cancel out. And then we're just left with x plus 1. And x plus 1 is the graph right here. But why is there a hole? Well, there's a hole because if you plug in 1 back into the regular function, you get 1 minus 1, which is 0, and then over 1 minus 1, which is also 0. So you get 0 over 0, and you get an undefined value. So that's why there's a hole at that point. Now, how do we know that the hole is at 2? Well, if we plug in 1 into the new function that we found right here, we can see that 1 plus 1 equals 2. So that's how we know that the hole is at 1, 2. And this function is the same basically as x plus 1, except there's just that removable discontinuity at the point 1, 2. And it's called removable because, as you can see, when we factored it out, we just removed the discontinuity right here by canceling out the like terms. Okay, so let's look at the first type of non-removable discontinuity. We have the infinite discontinuity. And here we have the function graph f of x equals 1 over x, okay? And this is infinite discontinuity. As you can see, the graph goes to infinity right here and goes to negative infinity right here. And at this point, when x equals 0, you can see the denominator equals 0, but the numerator is still a value. So that gives us an asymptote, a vertical asymptote at the point at when x equals 0. So that gives us a vertical asymptote. So infinite discontinuities always have vertical asymptotes. Vertical asymptotes. And they only occur when the denominator is 0, but the numerator is some value, some defined value, which is not 0, okay? And they're non-removable because, as you can see, this cannot be factored and you cannot remove the discontinuity. Like, you can't factor out the x and another x from the numerator and then cancel them out. So that's why they're called non-removable discontinuities, because they can't be removed, which is pretty intuitive. Now we have the second type of non-removable discontinuity and the last discontinuity that we will be talking about, which is the jump discontinuity. Now this is my best attempt at drawing this piecewise function right here, which is the function is x when x is less than negative 2, which is right here. And then the function is x squared when x is greater than or equal to negative 2, which is right here. Now this is called a jump discontinuity because, as you can see, there is a jump in the graph right here when x equals negative 2. So when x equals negative 2, we can say there is a jump discontinuity. And that's basically all there is to the jump discontinuity. If you look at a graph and you see a jump between maybe two parts of the graph, then it's going to be a jump discontinuity. Now this is a completely random graph that I've just drawn. Don't ask me what function this is because I would not be able to tell you. So this graph has all three different types of discontinuities. So let's see if we can name all of them. If you want to pause the video right here and see if you can name them for yourself, you can do that. Otherwise, I'll just do them right now. So the first one is right here. As you can see, there's a vertical asymptote, and that indicates that there would be a infinite discontinuity. You can also see that both sides of the graphs are going down here to infinity, or to negative infinity rather. So you can say that this is going to be an infinite discontinuity. And the vertical asymptote kind of gives that away. The second discontinuity is right here. You can see that there's a jump from this graph right here to this graph. So that would be a jump discontinuity. So this right here is going to be a jump discontinuity. And lastly, you can see that there is a hole right here in the graph. So a hole in the graph represents the removable or hole discontinuity. So that's going to be the removable slash hole discontinuity right there. Now, although there is a hole right here within the jump discontinuity, it jumps down to a different graph, which is why it's not removable. If there's just a hole, but it doesn't jump to a different graph, then it's a removable discontinuity. However, if it jumps, then it's a jump discontinuity. So these are kind of all three discontinuities in like one single graph. Hopefully that helps. So now that we've looked at all the different types of discontinuities, let's define what continuity at a point is. So the very basic, I guess, kind of intuitive definition of continuity at a point is just if you can go through that point without picking up, I guess for me it would be my marker, maybe a pencil or pen, whatever you're drawing the graph with, right? So if you can draw the graph without picking up whatever thing you're writing with, then it is continuous at that point. Now that's a very like kind of loose definition of continuity, but let's look at an example, right? So suppose this is the point C, the x value C, right? And we want to find if this function right here is continuous at the point C. Now you can see that I just drew that function and I did not pick up my marker once, even when I went through C. So that means the function is continuous at that point. Now let's look at a different function. Suppose we had the function like that. Now as you can see, I did pick up my marker in order to draw that function. So that function is not continuous at the point C. Now again, that's a very loose definition of continuity at a point. So let's look at a more rigorous definition. So the more rigorous College Board definition of continuity at a point is right here. So a function is continuous at a point, continuous if and only if the limit as x approaches that point, suppose at C, so is continuous at C if the limit as x approaches C of the function exists if f of C is defined. So f of C is defined. And finally, these two have to equal each other. So the limit as x approaches C of f of x has to exist. F of C has to be defined, and they have to be equal to each other. Now this looks pretty complicated, but let me try to break it down. So suppose we have the graph, let's say, suppose we have the graph x squared, right? So x squared right here. And we want to find out if the function is continuous at x equals 1. X equals 1, right here. So for this, I'll make that bigger. So for this, we have to first figure out the limit. So limit as x approaches 1 of x squared. And for this one, we can just plug in 1 into the function, and we would get the limit as x approaches 1 of x squared equals 1, right? And then we would also have to find what f of 1 is. So f of 1 in this case would just be 1 squared, which is 1. And you can see that 1 equals 1, so the function is continuous at this point. Now let's look at a different function. Now I'm just going to draw a completely random function. And let's do this. So suppose we have the function something like that, and then we'll draw a hole right here and put it right there. Okay, so we'll say this is 2, this is -3, and this right here is 3. So this is x equals 3, this is y equals 2, and this is y equals -3, okay? And we want to find out if this function is continuous at the point x equals 3, right? So first we find the limit as x approaches 3, of the function, we'll just call it f of x, right? So what is that? So we can see that if we take the graph and we approach 3 from both sides, so approach it from the positive and approaching it from the negative, we can see that it gets closer and closer to this value -3 right here. So the limit as x approaches 3 of f of x is going to be -3. Now let's see what f of 3 is. So f of 3 is obviously not right here because there's a hole right there, right? And we can see that there's a closed dot right there, which indicates that f of 3 is at that point. So we can see that f of 3 is 2, as indicated by the closed dot. So we can say that f of 3 equals 2. Now -3 is not equal to 2, so we can see that this function is not continuous at x equals 3. And this also follows the idea that if you can draw it without picking up your marker, then it's continuous, but if you can't, then it's not continuous. As you can see, when I drew this, I had to pick up my marker to draw this dot right there. So that's basically the rigorous definition of continuity at a point. Although I feel like if you just need to figure out if a function is continuous or not, then kind of the simple definition is easier. So that is going to be it for this video. I hope you found that helpful and enjoyed the video. If you have any feedback, please let me know in the comments. Otherwise, I will see you for the next video. Bye-bye.